welcome everyone to this Spark Meetup event hosted by Baidu USA. My name is James Peng. I'm the principal architect at Baidu. Today, me and some of my colleagues will share with you some of the experience that we gained by using Spark to solve some of our internal large-scale distributed systems. We will share with you some of the lessons we learned, and we will share with you some of the systems that we built on top of the Spark ecosystem to meet some of our internal application needs. Actually, we started to use Spark about a year and a half ago. And at that time, the first application or the first problem that we tried to solve is to facilitate the interactive query load that we faced internally. Actually, back to the Spark Summit in summer of this year in San Francisco, I shared with the community how Spark fits into Baidu's scale. During that talk, I presented some of our work to use Spark SQL to support the interactive queries. Just to recap a little bit what we presented in the summit. Essentially, internally, we're facing the problems that most of our internal PMs and engineers need to keep track of all the top business metrics. And actually, throughout the day, many of them need to keep track of the different queries or to get business insights to meet with some of the sudden events. Our old system was built on top of the Hive, essentially by running the Hadoop MapReduce. Most of the queries can take up to tens of minutes. So to solve this problem, we used Spark SQL, and we were able to finish most of the queries within half a minute. Actually, this is the layered cake diagram that I showed on the Spark Summit. Essentially, we used the tachyon as a cache layer to basically cache in the data to speed up the query processing. Then we built something on top of Spark SQL, and we also did some query optimization in the Spark SQL query plan itself. By deploying the system into the production, in a typical setup, that, for example, the example which I showed here, we use MapReduce to query 6 terabytes of data. Then for the same workload, we use Spark, and then we also use Spark with tachyon as a caching layer. This diagram shows that we were able to speed up the interactive query by 30 to 50 times. At the end of the summit, I mentioned a little bit about how we're looking into the future. Basically, a little bit glimpse of the plan that we had at that time. Essentially, besides supporting the interactive query load, our biggest pain point there at that time is to see how do we use Spark to support machine learning, because that's one of the biggest usage in our backend systems. To do that, we think there's 2 challenges. One is the performance, and we think the important thing is to possibly using heterogeneous computing, and also probably doing some new type of machine learning algorithms. The other is functionality. We really need to do deep learning and other types of algorithms to support the diverse needs of a lot of internal applications. So today's talk essentially is to see what we have done for the last 4 or 5 months to really make that plan, how we actually use Spark, what the work we have done on top of the Spark framework to really make the machine learning work. So the title of today's talk is we call it Spark 1. We really want to use it to unleash the power of big data intelligence. The problem is that a lot of the big data applications essentially needs to build intelligent systems for either doing prediction or recommendation. For example, if it's online commerce, you need to do recommendation of your products. And then for search or for ad system, you need to do a lot of predictions. And typically, this type of intelligent pipeline has many stages. For example, we need to clean up the user log. We need to do a feature extraction. Then it will be followed by many, many stages of model training. And we also do model evaluation. For large-scale applications, the different stages may be done by actually different systems. For example, it can be a MR, Hadoop MR. It can be some in-house machine learning platforms. So our goal is actually really trying to solve the problem of this complexity to really make the system much easier to run. And we think Spark, with its clean interface, would be a very good candidate. But to make Spark work with this type of big data intelligence pipeline, we think, again, as I mentioned in the last slides, we need to solve the functionality problems and the performance issues. Because, as we all know, a lot of the machine learning algorithms can be very expensive. So our goal is really to say, if we can use a single platform to handle all the pipelines of a big data intelligence type of application, and then we can add a lot of new functionalities into the system to really make it run much faster and it supports all kinds of applications. So this gives you a high-level diagram of what we were doing. Essentially, on the performance front, we did 2 things. One is we introduced deep learning capability into Spark, and then we implemented some of the faster algorithms than the ones in MLlib so far. And my colleagues will share with you some of our test results and some of our findings in those areas. We also try to use heterogeneous computing to use the hardware acceleration to make the training much faster, and we will share some of the experience on that front as well. Essentially, you can see that as we build the Spark 1 platform, we should be able to support most of all kinds of type of applications. Either it's a search, ads, or it's a O2O type of applications, or it can be an e-commerce, or it can be an image search. Actually, to make the talk even more confined, we'll use the Baidu image search as an example application to show you how we actually customized or enhanced Spark to support its needs. For example, the Baidu image search essentially is like a typical search to find related image. It also provides a browsing capability that you can browse related images. It has a PC version and has a mobile version as well. Currently, we have daily impressions in the order of billions. So essentially, the volume of the data and the number of daily active users is quite large. To really make the image search work, as I mentioned, the Spark One really targeting the big data intelligence type of applications. Within the image search product itself, it has at least two intelligent pipelines. One is the one to do image feature extraction and recognition, so that we will be able to understand some of the semantic meanings within a graph, within a photo, so that we can do ranking, we can do related search and ads much better. The other is that we actually have a pipeline to do the image ads CTR prediction. That's a typical online ads system. So with that, I'll let four of my colleagues to show you what we have done to really make the Spark One platform work, and some of the initial results that we have achieved. First, let's give Wei De to share with you how do we use deep learning capability to be incorporated into Spark.
Thank you, James. My name is Wade. I'm a senior engineer at Baidu infrastructure team, specializing in development of Spark infrastructure for Baidu use cases. Today, I'm going to talk about empowering the multimedia with deep learning in Spark One platform. Like James said, like Baidu image search is a very critical product within Baidu. We have like billions of page views, and typically for image search, the challenging part is that most of the retrieval process is based on text. Users supply the labels and metadata with images, and then they try to match the query only based on the textual information. But that's error-prone because some images don't have labels, and sometimes the label is mislabeled. So we need to find a better way to utilize the features embedded in the image so that we can better match the image based on the features. So deep learning has been very hot these days. As we all know, like traditional computer vision technique is only based on the human-crafted features. But deep learning provides an automated way to extract very interesting features from images. From this slide, the left one is like deep convolutional neural network. You can see as the level goes deep, the kernels extract from the training of the image for facial features become more and more complicated. It's very intuitive and very good way to get features from images. And researchers in Baidu has done very good work combining image features with text features. The middle architecture of the deep neural networks actually combines recurrent neural network with convolutional network and make the retrieval more accurate and more like the ranking of the correct images is much higher than traditional state-of-art neural networks. The one on the right is developed by another Baidu researcher, which makes the ranking of the image much accurate than traditional computer vision algorithms. So as I highlighted in the red box, these are the precision and the ranking rate for this. You can dive in the paper if you're interested. So for image search, the system is already very complicated. We have like ETL for log processing. We have corpus building and feature extraction for images. And we have interactive query system. So these three components is already have a very good performance in Spark. So in addition, Spark provides full stack applications on top of that, including like MLlib, Spark R, graphics, which is even better. But to facilitate large deep learning training, we feel like we need to implement on top of Spark for image indexing and ranking. So the goal and the requirement for the Spark 1 system is to have one single Spark cluster to have all the functionalities for the image search platform. And we want to do deep learning in a distributed fashion so that we can train models with billions of parameters, billions of features, and trillions of training examples. And we also need to address the scalability issues because we want this system to be generic enough so that it can be utilized by multiple developers, even a very junior developer can train deep learning models on top of the Spark cluster. And we want to make it reliable because training might fail in the middle. We want to be automatically recovered from training for deep learning models. And in addition, Baidu has a large cluster hardware which contains heterogeneous computing, which includes GPU, FPGA, and CPU. We want to have our resource utilization on Spark cluster to be more efficiently allocate resources for deep learning models. So we develop a common platform, especially for deep learning applications, so that users is able to submit training configs with executor specification, in addition with the hardware specification to train on the cluster. And the driver applications will keep monitoring the progress of each instance of the training and then reporting the classification errors and also the model validation results. And after training, the model will be saved to HDFS. So this is an example of the training. We utilize the parameter server paradigm to make the gradient synchronization in a distributed fashion so that it can scale up to billions of parameters. And we utilize the mini batch trainings so that it's already been proved it can convert very rapidly for large models. And the data is evenly partitioned across all the Spark executors so that it can do a mini batch within passes. Finally, I want to summarize that we have training pipelines which they can take care of data cleaning, feature extraction, and model training. And Spark already handles data sampling and partitioning. And it also has some functionality for feature engineering and hyperparameter tuning. That already supports very fast iterations for the model. We also want to emphasize that for the prediction pipeline, we have, since Spark already has a streaming and the batch process, we utilize the pipeline so that when the online ingestion of images coming, we can predict the models using the models in an online fashion. So by that, I think Chuan will talk about more on the feature extraction side, and for Chuning, we'll talk about on model training on heterogeneous computing. Thank you.
Anybody has any questions? Feel free to ask.
Oh, you have? Sure.
My question is how. Thank you. My question is how big can you scale the training? So there is a computation trade-off on the cluster, and it's kind of hard to overcome it in standard settings. And I wonder how big can you scale?
Yes, so basically, I think we train very large models with more than several billion features and more than 400 million parameters in a model. And the question, for the data partitioning, is really depend on the sparsity of the model, the feature dimension of the model, and also the data of the data size of the model. So I guess the number I gave you is probably the largest model. Okay.
Is Tachyon being used as a caching layer for this work as well?
No, Tachyon is not used right now for the deep learning training yet. Yeah.
Let me add more. We actually haven't used Tachyon as any caching or as a parameter server for this system yet, but definitely we're looking into it.
You can speak up. I can repeat your question if you want.
So I'm curious why you decided to customize CPUs or GPUs, and also what are the improvements you saw because of this?
So the questions will be addressed by Chu about GPU and heterogeneous computing. Yeah.
Stay tuned. Next talk we'll talk about it.
Yeah. Okay. All right. Let me give it to Chen.
Hello, everyone. My name is Chen, and today I'm going to present our effort to achieve, where is that? To achieve the multimedia data intelligence and analysis in SparkVine. So the interesting keyword in this title is probably multimedia. So it's very uncommon, I would say, to process multimedia on Spark. So the first question I'm going to answer is why multimedia? That's because in recent years, many major companies have accumulated a lot of useful multimedia data from the user. For example, the user's voice, their photos, their videos, and there are a lot of useful information inside those multimedia data waiting to be unlocked. And once unlocked, those information can certainly provide a lot of help to your business. So as you can see, since there are so many benefits in unlocking the secrets in those multimedia data, then the question we are asking in the first place is probably wrong. We should be asking the question is why not? Why not? What is really holding us back for processing those multimedia data? So there are really two reasons. The first one is the difficulty in analyzing those multimedia data, because those tasks are considerable more difficult than understanding traditional text. The second one is the difficulty in executing such analysis in a very large production scale. And I would also like to emphasize that for those two challenges, actually without solving the first challenge, it's not very meaningful to even talk about the second challenge. Because if you cannot even process those multimedia data, then to understand what's inside, then there is not much meaning to actually develop a framework to process them. But luckily, in recent years, there has been a lot of the development in the general machine learning domain, for example, in the voice recognition, in the image and video analysis domain. And we are actually coming to a stage to able to fully understand the contents of the inside those multimedia data for some real and practical applications. So suddenly, all of a sudden, the second task, the need to have a proper infrastructure and a platform to support such kind of execution of the analysis in large scale become very urgent task. And that's actually pretty much the focus of my talk. So just in conclusion, what I'm trying to say is it's time for the next stage. We have been digging text files, digging logs for many years. And right now is the time to move from the text format into the multimedia file to general binary format. And for a very specific business motivation, we have the Baidu image search business. And we have billions of images in need of the feature extraction and the transformation for many deep learning applications. For example, you have a group of images you want to classify to distinguish some product photos from those group of images. And after that, you want to do a ranking of those photos in order to select the single best photo to show to your user. And last but not the least, you want to do a CTR prediction in order to determine which is the best ad to show for a particular user. And for the particular case of the image search, it's very useful to actually including the image feature itself into the CTR prediction model. And my colleague Tianbing after me will actually talk more about the CTR production model training. And so that's all for the motivation. In order to achieve those goals, we found that there are generally three challenges. The first one is, for example, still take the image processing as an example. Just suppose you have one single image as the input, then what's your call functions to actually do the feature extraction on this one single image? The second one is if you have millions or billions levels of the image, how you efficient distributed execution of the feature extraction with the multimedia input supported. And the last one, we think is also important goal to achieve is to have a plug and play capability for any feature extraction program, even though those programs are never really designed for the Spark to run in the first place. But we want to also parallel distributed to execute those tasks. So I will talk about those three challenges and how we actually overcome them one by one. So for the first one is for the feature extraction call functions. So here is an example of what we are using in Baidu to actually extract some meaningful features from the image. Because this is a Spark Summit, I want to go into the detail of this C++ program, the internal logic about the feature extraction. But what I want to mention here is actually, as you can see, for one reason or another, actually the C++ program or the C++ language is actually very kind of like a common for people to do the multimedia data analysis understanding task. So, and in very common situation that the C++ program actually has a dependency on other C++ library. And down below, there are maybe some open source, like OpenCV library, even down below. What I'm trying to say is really, it's actually very difficult, or to say impossible, to actually rewrite all those complex layer after layers logic in Java or Scala, so that you can directly operate on Spark RDD. So in this way, the streaming in Hadoop terminology or the pipe in the Spark terminology is really the right way to go to support such kind of application running on Spark. And assume we can already run those programs on Spark. Then we can already run this program to extract the feature on a single machine. Then what's really the next challenge? Suppose we have input data on the left side, and the scale is very large, it's millions or billions levels of the binary files. And they are constantly changing and adding by the user, and we have the need to do a faster iteration of the whole system. Maybe we want the system to be more responsive to the user's need, or maybe we just want to try new algorithm to extract the features. And on the right side is the output we want. We want to extract the high-level feature descriptions from those images, or maybe we want to output some processed or transformed multimedia files, or maybe we want both of them. And so how we really make the system work end-to-end. One way is we just use the single machine method. We just use the C++ program I just showed you. You can connect the input with the output. And the problem is quite obvious. Just assume you only need 200 milliseconds to process each image to generate all the image features, and you have 16 tasks running perfectly in parallel on this one single machine. There is no computation for resource, there is no waiting, there is no failure and retry or whatsoever. And you only have 100 millions of images you want to process. But if you do the math, you will find that you will need more than 14 days to fully extract the feature from those 100 million of images. So that's definitely not acceptable for any practical business use. And a common way to speed up this, of course, is we want to distribute to 500 machines. But the problem is how we really manage such kind of distributed computation. There are a lot of complex problems, like how you split the input, how you distribute the dependency file, and how you feed the input to the user program, how you collect the output, how you handle the failures, how you do the retries, how you scheduling the task. The list just go on and on. So, but luckily, Spark to the rescue, right? We have Spark have already solved many of those challenging problems. We only need to link the missing piece so that to achieve our goal. So what we did is based on the Spark, we actually introduced this thing called a binary piped RDD in order to achieve our goal. So I want to go to the technical detail here about what is really inside this binary pipe, the RDD. But you are more than welcome to talk to me after the talk if you want to know the technical low-level details. But I just want to mention that the key function inside the binary pipe RDD, just like the name suggests, is actually to pipe the binary data into the user program and also collect the program's output as the original binary format. And as you can probably already imagine, this including things like how you archive the unarchived input first, and how you encoding, how you do the serialization, and after the user program, you do the reverse thing, right? You probably need to deserialize the decoding and then archive the output and put on HDFS, for example. So there's some logic happen inside. And I want to go into the source code level either, but in this slide, I just want to show the flexibility of the design. So basically, because of the nature of the task, we have a lot of optional parameter built into this, what we call the binary piped RDD. And those parameters actually provide us with a flexible output format. We can output feature vectors, we can output some ranking scores, we can output, for example, your transformed or processed binary files, or combination of some of them. And like I mentioned in the previous slide, the encoding and the serialization, all those things are quite important to this function. So you also have the flexibility to actually plug in your own code directly into the platform, into this RDD, so that maybe we actually provide pretty good serialization and encoding, decoding functions to accommodate common needs. But if you have a better version, you have a faster version, or maybe you have a version that is more compatible with your user logic, so you have the freedom to actually plug in. And another advantage I want to mention here is, as you can see, since all those serialization and encoding, all those technical low-level details are actually happen inside the RDD, happen inside the platform. So everything is actually distributed. There is nothing like you have to do an early preparation of the data, which may become the single bottleneck of the system. That means that the system has no bottleneck, no single point of computations, that the system is actually linear scalable, as I'm going to show in the experimental results. So for the performance test, we actually running a Spark 1 cluster, and we have over 11,000 of images as input with archive function on for the binary piped RDD. And we running a feature extraction on each image. So the feature extraction logic is exactly the one I'm showing you the C++ program in the very early slides. And we measure the end-to-end performance. I also mentioned the end-to-end performance actually including all the computational cost for both the platform and the user logic. So that's really including like how you distributed the dependency pile, how you feed the input, how you extract the feature, so everything is included. And we demonstrated the linear scalability of our system. As you can see with the number of the CPU cores increase, we have the computation, end-to-end computational time decrease linearly accordingly. And the formula we got from this initial testing is we can process 5.6 image per core per second, and the whole system is linear scalable. And going into production, back to my original example, if you have 100 million of image files you want to process, and you have 10,000 cores of the cluster for Spark, this is already a fairly large cluster in Baidu, but not the largest. But if you have such kind of computational power, you can actually process all those 100 million of image files within half an hour. This is compared to the more than 14 days we used to have. And so as a conclusion, we enable multimedia data processing on Spark 1 through the means of the supporting binary input formats plus pipe-based binary and library execution. And this is currently a missing functionality in Spark or previously in Hadoop. And it's our belief that this kind of functionality going forward is actually a very crucial part for any type of the distributed computing system. So that's all for my talk. Previous page. Yeah, actually, okay. So the question is really about the testing environment setup of this test. If I understand the question correctly, whether your CPU core is actually distributed among different computational nodes. The answer is yes. This is actually a fairly small, as you can see, it's a fairly small scale cluster. We basically have 3 worker nodes and 1 master node. And so basically the CPU cost we mentioned here is already distributed. It's not like we are running on a single machine and give the result. So there is definitely computational cost. You actually distribute all the dependency file, for example, into each node. So it's not like and I think maybe I also forgot to mention that in this initial test, we actually output both the processed binary and the feature vectors. So there are 2 different output. For the processed binary, we actually upload them into a co-located HDFS server. So basically, the end-to-end performance also including the time to save the processed binary even. But it's a co-located, it's a very low latency, of course.
So do you guys have any future plans of open sourcing this binary encoder to the layer 2?
Yeah, I think the plan, the answer is yes. We are plan. That's in the planning, and I'm very much looking forward to it. And right now we are very much focused on the really connecting, integrate this thing into our product. But after that, we will just clean up a little bit and make it ready for open source. That's the plan, actually, as far as I know. What you mean is actually the input data is actually multiple separate files. Is that your concern?
So do you mean since you allocate contiguous virtual memory in Java, but on disk, I mean, physical memory is not contiguous. Right. How do we optimize in that case?
Why in C, assume the memory is linear?
Mhm.
Handle that you have to make a copy, or you have to actually make disk, or you have to jump into a machine to choose the memory to allocate the disk. So which solution can you place on those problems?
I'm not sure I fully understand the question. So the question, sorry.
So this is the first step of our work. We are continuing optimizing our solution. We are not getting there yet. That's a very deep question. So, but we will get there.
Okay. Mhm. Mhm. Okay. Yeah. Actually, that's a very good question. That's actually to answer that, I go into a little bit to the technical details. So actually, the very first version of this feature, not the current version, we actually use the Spark context. There is an API called the binary files. So in that files, the return is an RDD of the pair type. And the first one is a string. The second value type is a portable data stream, something called that. And so the portable data stream is very much what you said. It's almost like a pointer to the HDFS file. So what each executor get is actually a pointer to the original file. It's not all the original file is loaded into the memory and distributed. So each executor actually is responsible for actually going into the HDFS, following the pointer, and to read the binary file chunk by chunk. Anyway, this is the first version. It's very similar to what you described. But going into production, that way simply won't work because you have millions or billions of the image. And how can you put millions or billions of individual binary files onto HDFS? It will just explode. So that's why I also mentioned that we have the archive function. So you need to have an archive of those individual binary files. Basically, your executor is responsible for passing 2 layers of the binary. The first layer is actually, or maybe I go too much detail, but the first layer is actually the archive layer. And then after that, you expose your real binary file. And then you do the processing. That's the current version we have.
So next, let's welcome Ning to tell you a little bit how we enhance the deep learning with the heterogeneous hardware. Maybe that answers one of the previous questions as well.
Hello, my name is Ning Chu, and I'm introducing how to enhance the deep learning in Spark 1 with heterogeneous hardware right now. And basically, we have seen that we have the Spark architecture and serving a lot of Baidu applications. And like the Spark SQL, deep learning, batch processing, streaming, all kinds of applications. And but there is all kinds of limitations in the current platform. As you know, that Baidu is really a big company with we just mentioned that we are doing like huge models and for the deep learning and involve billions of model parameters, features, and trillions of training examples. And so that's really not a simple problem to solve. I mean, for most of our company. And we see that performance is one of the top issue for us, and currently it is limited by the capability of the CPUs inside the servers. And also the scalability is another one, and we have current different kind of special deep learning platforms, but none of them are really at the large scale. So the question is, what if we can build something really powerful and on the larger scale? So on the Spark 1 and with Heterogeneous, we really want to leverage the heterogeneous hardware resource for the machine learning, deep learning at the scale of Spark. And for the hardware resource side, and we are thinking about the GPU and FPGA. And as we all know that the GPU is very powerful computing and suitable for this high density computing. And for FPGA, actually, is very quite flexible way, and it has very lower power consumption. But if we find the right workload, and we can really do the really good accelerations for the dynamic workloads. And for the FPGA, also is developed by our Baidu USDC compute team. So on the Spark side, and we want to solve the scalability issue, and we want to really run this platform on the thousands of machines. And also, we want to provide the multi-tenancy for this Spark, so we can run tons of applications at the same time for these different people and the different applications inside Baidu, so they can all share the same platform. So that's how we envision the heterogeneous computing on the Spark 1. We really want to empower the Spark with the GPU and FPGA, the different kind of the computing. And so we can serve the deep learning right now, but in the future, we want to also find the right applications in the SQL or batch processing or streaming, whatever the applications is running on this platform. So what do we build on the Spark 1 for this heterogeneous computing? So basically, first we want to do this dynamic resource scheduling. And we have adding this new resource for the GPU and FPGA. And basically, the application can request the resource just for the GPU and the FPGA, just like they are requesting the CPU and the memory. And also the resource allocation, we have built in with Yang to do this all kinds of resource allocation. And we build in with the containers so we can achieve this resource isolation goals. So it's basically very fit each other perfectly. And for the second part, we want to provide a very simple interface to the applications. So we create this new RDD. So with this new RDD, so just application can transparently benefit from this new hardware resource other than the CPU. And also, we want to use this very common and consistent interface for this. We use the OpenCL interface, so you can write the new kernels if you are adding the new library or new algorithm into the Spark library. And so, for example, so if like you want to write the whole pack, so basically you just need a Scala driver and a C++ program on the worker, and then a very regular OpenCL kernel, so you can run on the GPU or FPGA. So it's very simple. And here is the architecture of this heterogeneous computing. And basically, the application the user application, like the app master, will first request the resource from the Yang. And so basically, we add the GPU and the FPGA to this part. And so the application can request this just like the regular resource. And then Yang will allocate the containers to this application. And then it will start all these containers on, with the app slave on the workers. And it depends on the application's requirement, and the container could use the Java native interface, the JNI, to call into the C++ program, and then it will eventually call this OpenCL kernel on the GPU or FPGA. So basically, this is the flow to go. And just some simple results here. And first, I want to show you, and you can see that this is just on one node, but we want to show that how powerful the GPU is. Just do a simple ANN training, and with different, on the x-axis is the how many paths we do, like the 100, 1,000, and 10,000. So on the y-axis is the runtime. So basically, you can see how powerful the GPU is, and as we know. And for the scalability, and you can see that we run another experiment. It's the distributed deep learning training latency per pass. The experiment is the convolutional with the 10 layer. It's for the image classification. And on the x-axis is the number of GPUs we have for this experiment. And for the y-axis is the number of seconds. So for each pass. So basically, you can see that with the number of the GPU increasing, we have almost the linear effects for this performance. So it's scale very well right now. Yeah, so that's it. So any questions for this part? The PGA is just something we are under development for the hardware team yet. We don't have much detail right now, but we definitely will reveal something maybe next year. You mean what's the GPU used for, right? It's kind of used for some algorithm or could use for some accelerated the whole architecture. But yeah, it's still very confidential so far. Sorry. Yeah, please.
Will you be open sourcing the changes you've done for PRDD and to Yarn to access GPUs?
Yeah, we definitely planning to do that, but right now it's still in the early stage, and we are doing this production right now. And after the production is ready, probably we will consider this step. Yeah, please.
My question, but how many changes did you make? Can you go over some of the changes you made in the RDD? Were they a lot?
I don't have this number yet, but right now we do have had a lot of for this RDD. Basically, you see there's a lot of things undergoing there. Like if you want to transfer the data, I mean, from the CPU to the GPU, and you don't want the applications to do this. So basically, you want to transfer the data transparently, just like what CUDA does. So yeah, there's a lot of code handling these complexities, but it's very simple interface. Yeah, I need to count that number, I think. Yeah, please. No, we don't preserve the data, I mean, inside the GPU yet. Basically, right now we use container, and we can assign the dedicated hardware resource to each container. So, yeah. But we don't have this kind of the fully virtualized GPU, so we can share with all the workload at runtime. It's not there yet. Yeah, but we definitely want to do that in the future, I think. Yeah, please.
Do you run stochastic gradient for training?
Excuse me. New. Yes, yes. Yeah.
How do you parallelize
STD.
How do you do parallel?
Oh, you mean the parallel computing for these models? Yeah, I think it's something like we talked in the first talk. We do this split the data and do this parameters inside each of the node. Yeah. So.
Maybe I will just cover the synchronous SGD, asynchronous SGD. Like you can read some papers published by Limu and also CMU. They talk about how to do mini batch for distributed SGDs. Does that answer your question? I just want to, because there are so many complicated details, I don't want to go into. Yeah.
So basically, my question was, like, you can definitely have very well parallelized, but then the convergence will be very bad. So my question is, actually, how good is the convergence with the parallelization?
Yes, like I mentioned, the SSP paper and BSP paper talk about convergence. They prove that it's definitely the good way is synchronized SGD, right? But it hurts the performance a lot. But asynchronously, you have to make the pass, like how longer the toleration of the pass, so that you can make the convergence trade-off. Does that make sense?
Yeah, so you basically use this paper.
Yeah. Yeah.
Thank you. So next will be my colleague Tian Bing for this next talk.
Okay, so my name is Tian Bing. So I'm working at GM's infrastructure group here. So this work is collaborated with Chuan Wang. Basically, I just introduced a very highly optimized logistic regression for model training in Spark 1. So basically, this is a training pipeline for CTR prediction. So image search, the basic application is image search at CTR, click-through rate prediction. So we have impression queries and clicks. And we also have image features. So we just combine these features and we just use feature mapping to transform the very high dimensional feature space into low dense feature space. And these low dimensional features feed into our logistic regression model training for CTR. And after that, we are able to do the model evaluation. So this is the basic at CTR training pipeline. So basically, because we have a very hard requirement, basically there are two requirements. One is scalability, another is performance. So here we have a large scale of data. For example, we have 10 to 100 terabytes training data. And the dimension space is very huge. For example, it's about 100 billion. And but at the same time, we have very high requirement for the performance. So we need to train the model daily within 10 hours. And also we need to achieve the very accurate model prediction. So our target AUC is about 0.85. Okay, so we also do some survey on MLlib logistic regression. So basically there are two kind of algorithm. One is HGD, but HGD's disadvantage is that it compute inexpensive, but actually it has very slow convergence rate. So it's not able to achieve our desired high accuracy. Another very good algorithm is LBFGS. Actually, LBFGS has a linear convergence, and it's able to achieve pretty high accuracy. However, it's not able to scale to very large scale data, especially for very high dimension, because actually it needs some storage for the last M gradients. So this is it needs some like the memory consumption about MD. D is the dimension of the model, and the M is the last M. And also we just do some test running, and it crashed with 400 gigabytes data. There's basically some memory issues here. So what we did? Actually, we just developed a fast and accurate logistic regression algorithm while we still maintain inexpensive computation and we have superior scalability. So our model is able to train 10 terabytes data in only 150 machine clusters. We are able to achieve more than 10x acceleration speed up compared to the very computational inexpensive MLlib SGD. We actually, in terms of the accuracy, we are able to achieve very high accuracy, more than 0.85. And actually, this algorithm usually converges within 100 to 200 iterations to achieve design accuracy. So actually, what we did, we just used the conjugate gradient. So for example, here, so this is our curve. So we just plot this convergence rate based on our real data. X-axis is number of iterations, so approach. Y-axis actually is precision. For example, the f object function minus the minimum of the object function. So actually, it's very clear. So conjugate gradient has a linear convergence. And actually, BFGS, this is an MLlib implementation. It's also have very good convergence rate. However, it's not so competitive in high-dimensional space and also in this real data set. Actually, conjugate gradient actually the number iteration equals the number of eigenvectors, different eigenvectors. So in this not so close related data. So we have very small number of distinguished eigenvalues. So that's why it converges so fast. And obviously, the SGD is too slow. So this is actually regarded a very small data set for us. I will show you some really big data set. This is the first result. We just test our result on 1.2 terabytes data. And we have about 0.5 billion number examples. And we have feature dimensions. The final feature dimension after feature mapping, after the dimension reduction, we have 350,000 dimension. And the test data is about 10%. And finally, it just takes us less than half an hour training. And we are able to achieve very high accuracy. Compared to the MLlib, actually MLlib has not a very good representation of the feature. So it has suffered a lot of memory issues because this cluster is very small. You see, it's around 60 nodes and only 20 gigabytes memory for each node. So that's why MLlib running so slowly. Actually, they are running with the same number of iterations. And actually, this accuracy is not satisfied our requirement, so we just gave up. And also, this is even more big data. So we just test our data on about 150 nodes, and it's about more than 700 cores. Actually, we have not enough memory because these are very accommodative machines. We have not so advanced machines now. It's about 30 gigabytes memory per node. So actually, we are suffering from limited memory. But this is on this media-sized cluster. We are able to train 30 terabytes data. And the number example is about 5.7 billion. And the dimension actually is more than 100,000. We also have another experiment on like 200,000 dimensions. And the running time is about 4 hours, 4.2 hours. And the testing data is also very huge. So actually we are able to achieve very high accuracy. So, okay. So that's the major results. I think, I'm not sure what's the current record in the community, but I think this is a very amazing results. Yeah. Okay, how we achieve it? Actually, yeah. So what kind of optimization we are using? Optimization algorithm. And we are just also doing a lot of some tricks on the computation optimization. We just reduce the computation because a lot of unnecessary computation is just avoid. And when our problem come to a certain large stage, for example, when we have more than terabytes data, the program we have some memory bound program, and we tune our the garbage collection, and we also redesign our feature representation, like make it compact, and we also make the model compact, so solve the memory bounded issues. And actually, we also introduced some mini batch techniques. The two disadvantages that one is it's able to reduce the number of, it's able to reduce the training time, because at each time we just train the submodel on small number example, not small number example, but just some fraction of number examples. And another advantage is that we are able to aggregate these models. And so it's possible to boosting the prediction accuracy. But actually there's some trade-off, because if we have larger number of batches, it will introduce more heavily combination cost. Then the total training time will increase. So we need to tune the number of batches. And also we need to tune the number of iterations per training like the submodels. And also, we also provide the sparse model support, because many problems actually the data are sparse. So it's not necessary to just the model are sparse. Not necessary to use very dense vectors. And we also have very amazing results here. And for the time limit, I think I just mentioned the first two. So what kind of algorithm we are using? It's very simple. We are using very classical algorithm with some new advancement. We are using conjugate gradient. The algorithm is very long-term ignored, but actually it has very strong global linear convergence guarantee, and locally it has superlinear convergence rate. And what's a bigger advantage is that it has very inexpensive computational cost per iteration, comparable to the HGD. So that's very good, because it's linear convergence. To achieve epsilon accuracy, we only need a log of one epsilon number of iterations. And that's why we are able to achieve very high accuracy. And for the dense model, the time complexity, overall time complexity is just proportional to the number example multiplied by the dimension of the model. For the sparse model, this is just NZ. So, and also another advantage compared to the LBGFS, it works very well for high dimensional problem. For example, Andrew has just did some related research on neural nets. And also many literature just discuss this problem. The basic logic is that because the number of iteration to converge is just determined by the cluster structure of the spectral norm. So actually, if we have very high dimension, but it's not unrelated, it's weak related, we are able to achieve we are only need to not too much iterations. That's really advantage here. Okay, so another thing that we spend a lot of effort to do the computation optimization. So for the time limits, I just mentioned a little bit. So actually, the Heisen matrix is a closed form. So it is really very easy to calculate. But we are not really calculated, because we are just trying to calculate the search direction transpose, the Heisen matrix and the search direction. So actually, it's able to just simple reduction into the inner product. And for the inner product, because we have compact representation of the features, so it's just a simple addition. So actually, we are reduce the heavily matrix vector multiplication into like the 1 or 2 cycle CPU addition. So that's the major advantage over here. Okay, so I think, yeah, that's what do you have any questions? Okay, so let's welcome James for the final.
All right, again, thanks everyone for coming. Essentially, today, me and my colleagues shared with you some of the work that we have done for the last 4 or 5 months. Our goal is really to build a Spark One platform to support all kinds of big data intelligence type of applications. We share with you that for a traditionally multiple staged intelligence pipeline, we were trying to solve using Spark as a single platform to really perform every tasks of this pipeline. Some of the highlights of today's talk, essentially we introduced deep learning capabilities into Spark to make the functionality much more rich. And we also introduced massively parallel processing of the multimedia data. In terms of the performance, we used hardware acceleration to achieve more than 10x of speed up. Also, Timmy just introduced with you, we have a super fast logistic regression that can support very large models. Again, thank you for coming. This is just the initial work. As I mentioned, it's the work about 4 or 5 months, where we'll continue to work on many components of this system, and some of the packages or some of the algorithms that we introduced today, as we gain more experience in production, in our own production, as we clean up the code, we're actually more than happy to contribute some of the work that we have done back to the community. So at the end, I'll let all my colleagues coming up, and if you have any further questions, we're more than happy to answer them. Also, you're welcome to stick around a little bit to social, or they probably still have some drinks left. You can grab a drink and talk to us.